50 years and 4 days ago, Neil Armstrong placed the first man's foot on the moon. And along with them on that trip were 2 heat sources that Mound built. So in honor of that historic event, I'm going to take you all on a walk down heat source memory lane. Starting out back in 1954, Ken Jordan was working on a project to see if he could generate electricity using a heat source to drive a steam engine which drove a generator. That was turning out to be a challenge, that the generator was requiring more output than they could generate with the heat source there. At lunch one day with John Burden, they were talking about that problem, and they came up with the idea that they could use a thermocouple-like device, flowing heat through it, to generate electricity. The story is they just did calculations on a napkin, went back to the lab, in a few hours confirmed in their own minds that this would work. A couple of weeks later, they had created a device that generated 1.8 milliwatts of electrical energy. That was the proof that allowed them to proceed to get a patent on the device, which occurred in 1959. They also subsequently got into inducted in the U.S. Patent and Trademark Hall of Fame as a result of that invention. In 1959, with a device that the converter was built by the Martin Company, and Mound was the producer of the heat sources, and the first one that was demonstrated to President Eisenhower was fueled with polonium-210. And he was so impressed with the potential for this technology that he made it the centerpiece for his Atoms for Peace program. The DOE in earlier years, in about 1955, established what they called the Program for Systems for Nuclear Auxiliary Power. That's an acronym that will be carried through on a number of these systems. So the first application of a radioisotope thermoelectric generator in space was on the transit program of navigational satellites, a Transit 4. In 1961 was the first launch. That launch almost did not occur because the State Department was the authorizing agency, and the previous launch scheduled before this one was, well, it aborted and it crash landed in Cuba. But the State Department was a little concerned that this could happen again and drop a radioactive package on Cuba, and we'd have an international incident. So they were dragging their heels and weren't going to approve it. Well, Dr. Seaborg, who was the head of the Atomic Energy Commission at the time, was so enhanced with this program that he went to President Kennedy and got Kennedy's approval to go ahead with this launch. So 2 of these were launched, and both were successful in terms of their performance. They were a supplementary power supply on these satellites which had solar panels on them, but it demonstrated that this system would survive launch and could perform in space. During that time period in their early performance, there was an atmospheric atomic test which caused degradation of the solar panels, and as a result, they were still able to monitor the RTG's performance, and they continued to perform as planned. And actually, they continued to operate even after the satellites quit functioning. One of them operated for 15 years, and the other one operated for about 10 years. So the second use of RTGs was on the follow-up program for navigational satellites, the Transit 5. And the new program, heat source, was called the SNAP 9. And those were launched in 1963. The third unit actually failed to achieve orbit, and it burned up on re-entry. And that was the planned way to demonstrate the safety of these units. The fuel, which was plutonium metal, burned up in the atmosphere and dispersed so widely that it was not going to cause any kind of a health issue. Well, I guess DOE had, or not DOE, Atomic Energy Commission at the time had second thoughts about that from a safety perspective and a public relations perspective, and they changed their philosophy to what was called an intact reentry heat source. During this time, this technology created a lot of enthusiasm and a lot of ideas on how it could be used in different areas. So there were military applications that were looked at, there were medical applications, and a number of different space applications. The big thing that Mound contributed, and it's our responsibility, was to build the heat sources, was to use our scientists to develop the different fuel forms that were required for these various systems. Here we show that plutonium metal was used. We had plutonium zirconia, a program that used gadolinium polynide, plutonium-238 microspheres, shards, plutonium molybdenum cermet, and plutonium-238 dioxide, which was the latest fuel form that was used. Not only that, we had engineers working with a number of highly technical materials that weren't always the easiest to work with. They had to determine ways of machining, forming, and welding these. This is an extensive list of the materials that were used on our heat sources. In the military area, here's a list of the programs that supported military programs. The SNAP 15 heat source had 3 different designs that were worked on. More interesting, you'll see Swimsuit Heater. We have an interesting picture of an individual working at Mound that modeled that system, and on down the line. We'll show a little bit about each of those. Here are pictures of models of the SNAP 15, SNAP 15A, B, and C. And these were generally low wattage units, about 1 thermal watt. SNAP C was a little over 7 thermal watts. The MC 2012 was kind of unique in its design in that the heat source was suspended from the thermoelectric elements in the middle of this unit, and it had 2.1 thermal watts in it. Here's the swimsuit heater that the heat source design on the side was about 105 thermal watts. 4 of those went into the heat transfer device, which then pumped warming liquid through the suit that went underneath the rubber suit that the divers would wear. While only 1 unit was produced, so it appears that the Navy didn't decide that this was going to be something that they were going to carry on into the future. And by the look on the guy's face there, I would guess he wasn't too thrilled about wearing it. Milliwatt generator program was quite a strong production program here at Mound. It had 4.5 thermal watts, but we made, I think, 1,752 of these units in the production cycle. Transit Triad was a Navy navigational satellite. The heat source in this is a direct copy of one that was used on the Pioneer program, and I'll show you a little bit more about that later on. Another heat source for the Navy used in underwater applications was the Navy heat source. That was, I believe, 18 thermal watts, the triply encapsulated, which is kind of a typical design for these heat sources. The Hpg Mod 3 uses the technology that was developed for a space application with the multi-100 watt heat source in it. There are 2,400 thermal watts in that heat source, and in this device it produced 180 electrical watts. This was designed so that it could operate in both air and underwater, and the design could withstand 1,200 psi of hydrostatic pressure. And finally, the 5 watt RTG used the heat source technology that was generated in the general purpose heat source program. The 2 of the fuel clads in a graphite impact shell were placed inside of this unit to produce 5 electrical watts from 125 thermal watts. moving into the medical arena, Mound got involved in making heat sources for an artificial heart, pacemaker, and a miniature X-ray. The artificial heart heat source looked like this. There was a 15 watt and a 25 watt that were actually implanted in dogs, and they were implanted for about a 2-year time period to study any physiological effects that could result from those. The heat sources were then removed after those 2-year periods. In the pacemaker, shows here the heat source and a model of the pacemaker. Back in the late 60s and early 70s, battery technology was not very good. You could have a battery life in a pacemaker that maybe was 2 to 3 years long. By going with a heat source approach, you could get up to 10 or more years, and that would alleviate a lot of the surgical requirements to do that. This program really didn't last very long. There were concerns ultimately about long-term physiological effects, and I presume there were concerns that if somebody passed away and you didn't realize that they had a pacemaker of this nature in them and they went for cremation, that would cause a problem with the release of radioactive material. The X-ray source was generated at a time when there were concerns about lead poisoning in people's blood. And this X-ray source was going to be used in an X-ray fluorescence test device, which would allow you to use just a couple of drops of blood to find out whether or not that lead contamination was there. Apparently that didn't turn out to be something that was widely used either, because we only made 2 of these sources. Now, in a different application for space, we had rocket thrusters, we had water recovery and waste management systems. The Poodle was a heat source that was designed originally for use on a rover program. We made 3 of them, and that was it. The DART program was a program for ammonia thrusters, and the first set, they had problems with the fuel and the tubing, so that didn't work, but they came back with a second design, and the testing was successful for that, but we were never called upon to produce any for actual use in the spaces. Here's a copy, a picture of both the Poodle and the DART heat sources. Then the life support system, with man in space program progressing, there was a desire to look at trying to recover waste moisture in the capsule in terms of whether it's reprocessing urine or perspiration from the astronauts. And these were designed to support that. Again, I think we only made 2 of these, and obviously that didn't end up, they must have found a better way to do it than using these heat sources. And finally, Right 1 and Right 2 were heat sources that were used to handle. One was to pyrolyze solid waste, and the other was for water conditioning. And we made 2 of those. So these were experiments where they were trying things out and decided apparently there were better ways of doing it. So NASA's first effort at using an RTG was with 2 meteorological satellites called Nimbus satellites. They used what was called a SNAP 19B heat source, and the first one was launched in 1968. The booster rocket failed, and the system came down in the Santa Barbara Channel, leaving the heat sources in about 300 feet of water. The good thing about this, even though it was an aborted test, was that it demonstrated that the intact re-entry heat source design worked. We see a picture here of the 2 heat sources that were recovered out of 300 plus feet of water, and eventually the material was able to be reused. The second Nimbus launch in 1969 proved to be successful. The SNAP 19 program was an evolution of the original SNAP 9 heat source that was used on the Transit 5 navigational RTGs. The initial design called for a metal fuel form. Then as they started worrying about the intact reentry heat source issue, they went to microspheres, and finally with the intact reentry heat source design, went to a domed capsule with a graphite aeroshell to protect it, as well as the microsphere fuel form. The SNAP 19C was kind of a little bit different animal, and I think in the past we've had a presentation here about that. That was a unit that was used for remote telemetry. It was in the Himalayas, looking at our Chinese friends and what they were doing with their adventures there. So, with the Apollo program, there was a desire to do an investigation of the moon, in that a lot of scientists were concerned or curious about what the moon was constructed like. Does it have a core like the Earth does? Does it have something else? And so the seismic package was one that won one of the contests to be on there. They also had a laser reflector that was going up on the moon as well. So this seismic experimental package looked for seismic activity on the surface of the moon. It could detect meteoroid impacts, any oscillations of the moon in orbit, and variations in the directional strength of gravitational fields. So the problem was that the seismic instrumentation was sensitive to the temperatures of the environment. On the moon, the nighttime is 14 Earth days long, and it can get as cold as 184 degrees centigrade below zero. So that was an issue that they had to deal with, and the way they dealt with it was for Mound to provide two 15-watt heat sources on the Apollo 11 mission. That would maintain the temperature of that scientific package at a minus 54 degrees C. One of the things you can see here is that there are solar panels on that seismic package, so that data could only be transmitted back to Earth when it was daylight on the moon. And you can barely see on here where those heat sources are, but I brought one along so you can get an idea of just what the size of a 15-watt heat source on the surface of the moon would have looked like. Following the Apollo 11 mission, we had Apollo missions 12 through 17 that carried a lunar surface experimental packages. Those were powered by a SNAP 27 heat source that was produced here at Mound. That heat source had 1,480 thermal watts, producing about 70 electrical watts. Now that mission had a requirement to operate for 2 years. As it turned out, those systems on the moon were allowed to operate after the mission ended. The mission ended in '72, but they kept them operational until 1977. That gives you kind of an idea of the reliability of these systems. And you remember Apollo 13 mission had to be aborted. And on the return to Earth, they separated the lunar excursion module from the command module, and it burned up on re-entry into the Earth. Well, the heat source ended up in the Tonga Trench in the South Pacific, which was about 5 or 6 miles deep. Efforts to recover the heat source failed, but they were not able to detect any indication of any radioactive material in the area where it entered. So they felt very confident that once again the process of an intact re-entry heat source design was successful. And the way they worked that on the lunar module was there was a graphite container in which the heat source was housed. And on this picture you see Alan Bean removing the heat source from the LEM, and the RTG converter is on the surface of the moon there near his feet. Here's a model of the SNAP 27 heat source showing its components. and that's the RTG that it operates in. So I mentioned the Transit Triad mission previously, and the Pioneer mission used a SNAP 19 heat source that went through another iteration. It had a pressure relief device in it, and its fuel was changed from microspheres to a plutonium molybdenum surmet. That system produced in the RTG about 40 watts of electrical power. So with the Pioneer program, Pioneer 10 and Pioneer 11 launched in 72 and 73, were set to explore the outer planets of Jupiter and Saturn. The original mission requirement was for the system to operate for 21 months. Pioneer 10 was also the first spacecraft then to navigate through the asteroid belt, which had never been accomplished before. So when Pioneer 10 reached its destination of Jupiter, it actually had more than 22 watts of power available to it above and beyond the mission requirements. That allowed the scientists and managers of the Pioneer program for Pioneer 11 to look at going beyond Jupiter and flying on to Saturn. When Pioneer 11 got to Saturn, it actually had 30 watts more energy, electrical energy, than was required to support the mission at that time. Now again, the mission requirement was for 21 months, but in reality, Pioneer 10 was able to operate until 2003, and Pioneer 11, they lost communications with it in 1995. So once again, the reliability of these systems is proven to be exceptional. And each of these spacecraft actually had 4 of the SNAP 19 RTGs on them, providing them with 160 watts of electrical energy. Here's a picture of Jupiter as Pioneer 10 approached it and passed by it. These were taken at the closest of about 80,000 miles. Then Saturn was taken by Pioneer 11, was taken at about 13,000 miles. Using the same SNAP 19 RTG that supported our next goal of exploring the surface of a planet. And it turns out Mars was the obvious choice because there had always been some thought that there could be life forms on Mars, there could be water on Mars, and we wanted to determine if that was there. Viking 1 and Viking 2 each had 2 of the SNAP 19 RTGs on them. They were launched in 1975. Their mission requirement was to operate for 90 days. As it turns out, one operated until 1980 and the other until 1982. Again, a rousing success story in terms of performance. Missions became more demanding, needed more power, and they were looking for more efficiency in terms of power to weight. The way they were going to achieve that was to change from lead telluride-based thermoelectrics to silicon germanium and higher operating temperatures. That created the multi-100-watt heat source. It was built around the idea of a 1-inch diameter plutonium-238 dioxide ball encased in graphite, encased in a graphite aeroshell, and each of those balls contained 100 thermal watts of energy. 24 of those were in this configuration, providing 2,400 thermal watts of energy, which could be converted to approximately 160 watts in the RTG. So the first mission to use multi-100-watt was 2 Lincoln experimental satellites that were used for communications launched by the Air Force. Each of these satellites, they had solar panels on them, but they ended up with these didn't have solar panels. I went backwards a little bit on that, sorry about that. But they had 2 of the GPHS RTGs on them to provide their power. And it turns out that while they were launched in 1976, they were still operational during the first Gulf War in 1991. So around that same time, scientists recognized that there was a rare event coming up, that the outer planets were going to be in an alignment that would allow us to send spacecraft out there to investigate the outer planets. So the Voyager program was launched with, in 1977, with Voyager 1 and Voyager 2, each having 3 GPHS, multi-100 watt RTGs providing the power on them. These spacecraft went out to Jupiter, Saturn, Uranus, and Neptune. And here we see pictures taken by the Voyager spacecraft. After the Voyager mission, the Department of Energy, being concerned about security issues around plutonium-238, changed the responsibilities of various organizations that were involved in these programs. So Savannah River still produced the plutonium dioxide. Mound originally pelletized the fuel and encapsulated it, but the pelletization process went back to Savannah River as well as the encapsulation. Mound had produced the iridium hardware that was used to encapsulate the fuel. That responsibility went to Savannah River. The design and fabrication of the converter was done by the systems contractor. That continued to be the same. However, the responsibilities that the systems contractor had previously in assembling and acceptance testing, as well as shipment of the RTGs, came here to Mound. And that was all in conjunction with the new program design called the General Purpose Heat Source. Here we show a picture of a pressed plutonium-238 pellet, the GPHS heat source sitting just after its containment can was opened up, glowing red. Each of those pellets produced about 62.5 thermal watts. There were 4 of them in each of the heat source aeroshells, giving you 250 thermal watts. 18 of those went into the converter to give the RTG about 300 electrical watts at fueling time. This system went through extreme safety testing to address almost any accident scenario that one could imagine. There are multiple layers of graphite containment. The aeroshell was designed in such a manner that if there was a re-entry accident, that it would tumble and ablate evenly and survive impact on any surface here on land. So the first program that we supported with the Galileo mission was a mission to Jupiter. It was originally scheduled to be launched in 1986, but the shuttle disaster that happened then was launched just prior to the one we were scheduled to be on, caused a 3-year delay in the program. So Galileo launched in 1989 to study Jupiter and its primary moons, Io, Callisto, Ganymede, and Europa. So this mission was really quite successful. It was terminated in 2003, and it was terminated by flying the spacecraft into the surface of Jupiter because of concerns that Europa might have some life forms available on it because of the frozen oceans on its surface. This spacecraft had two GPHS RTGs on it. Here we see a picture of Jupiter with its giant red spot and the 4 moons. And one of the very rare events that Galileo was able to see was when Comet Shoemaker-Levy 9 crashed into Jupiter's surface. The second mission supported by GPHS was the Ulysses mission, which was primarily a European Space Agency mission, but we supplied the RTG before. It was launched in 1990, and it was a mission to study the heliosphere from a perspective that had never been done before. The intent was to fly the spacecraft over the poles of the sun. In order to accomplish that, they had to fly the spacecraft out to Jupiter using Jupiter's gravitational field to pull it into an orbit perpendicular to the plane of the planet so that it could fly over the poles of the sun. The mission was completed after 3 complete orbits over an 18-year time period, and the mission ended in 2009. The final mission that Mound supported with 3 GPHS RTGs, the Cassini mission, launched aboard a Titan Centaur rocket to study Saturn and its moon Titan. This was the largest spacecraft that we have launched. Launched in 1997, and that mission ended in September 15th of 2017. And again, this was a case of the mission was ended by flying the spacecraft into the surface of Saturn. There were 2 issues there. Titan, we thought, may have some potential of a different kind of life form based on the methane and elements in its atmosphere. And then there's another moon, Enceladus, that appeared to have water on it. So there's actually 2 moons around Saturn that they suspect there could be life forms on. So they chose to fly the spacecraft into the surface of the planet. Here are pictures of the moon Titan, the surface of Titan. There was a Huygens probe that the European Space Agency built for this mission, and then some other pictures that Cassini took of Saturn. One of the workhorses of the heat source program turns out to be this little 1-watt heater that Mound made that was plutonium-238 encapsulated in platinum rhodium with multiple layers of graphite containment. That supported the Pioneer program, the Voyager program, Galileo and Cassini, and even Spirit and Opportunity, which were powered with solar panels. They still had 3 of these heat sources on them to maintain proper temperatures or safe operating temperatures for the instruments that were on board. So, what did Mound contribute to all of this history? The technology was invented and patented here. We built nearly 2,500 heat sources, processed 190 kilograms of plutonium-238 into different fuel forms, assembled and tested 7 GPH RTGs to support 3 missions, produced heat sources for 44 RTGs and 25 space missions, assembled and tested 2 Hpg Mod 3s and 4 5 watts. And we almost had the program stay here. We were successful with DOE making that decision until 9/11 occurred, and then the decision was made to move the program out to Idaho. Any questions?